Chapter 4. Excess carriers in semiconductors. Objectives. 1. Understand how photons interact with direct and indirect bandgap semiconductors. 2. Understand generation recombination of excess carriers, possibly through trap sites. 3. Introduce quasi-Fermi levels in non-equilibrium. 4. Calculate diffusion currents from carrier concentration gradients and diffusivity. 5. Use the continuity equation to study time dependence of carrier concentrations. Most semiconductor devices operate by the creation of charge carriers in excess of the thermal equilibrium values. These excess carriers can be created by optical 1 excitation or electron bombardment, or as we shall see in Chapter 5, they can be injected across a forward-biased p-n junction. However the excess carriers arise, they can dominate the conduction processes in the semiconductor material. In this chapter we shall investigate the creation of excess carriers by optical absorption and the resulting properties of photoluminescence and photoconductivity. We shall study more closely the mechanism of electron-hole pair recombination and the effects of carrier trapping. Finally, we shall discuss the diffusion of excess carriers due to a carrier gradient, which serves as a basic mechanism of current conduction along with the mechanism of drift in an electric field. 1. In this context the word optical does not necessarily imply that the photons absorbed are in the visible part of the spectrum. Many semiconductors absorb photons in the infrared region, but this is included in the term optical absorption. An important technique for measuring the bandgap energy of a semiconductor is the absorption of incident photons by the material. In this experiment photons of selected wavelengths are directed at the sample, and relative transmission of the various photons is observed. Since photons with energies greater than the bandgap energy are absorbed while photons with energies less than the bandgap are transmitted, this experiment gives an accurate measure of the bandgap energy. Figure 4.1 Optical absorption of a photon with Hn7 e.g., A. An electron-hole pair is created during photon absorption, B. The excited electron gives up energy to the lattice by scattering events, C. The electron recombines with a hole in the valence band. It is apparent that a photon with energy Hnu e.g. can be absorbed in a semiconductor, Fig. 4.1. Since the valence band contains many electrons and the conduction band has many empty states into which the electrons may be excited, the probability of photon absorption is high. As Fig. 4.1 indicates, an electron excited to the conduction band by optical absorption may initially have more energy than is common for conduction band electrons. Almost all electrons are near EC unless the sample is very heavily doped. Thus the excited electron loses energy to the lattice in scattering events until its velocity reaches the thermal equilibrium velocity of other conduction band electrons. The electron and hole created by this absorption process are excess carriers. Since they are out of balance with their environment, they must eventually recombine. While the excess carriers exist in their respective bands, however, they are free to contribute to the conductivity of the material. A photon with energy less than e.g. is unable to excite an electron from the valence band to the conduction band. Thus in a pure semiconductor, there is negligible absorption of photons with Hn6 e.g. This explains why some materials are transparent in certain wavelength ranges. We are able to see through certain insulators, such as a good sodium chloride crystal, because a large energy gap containing no electron states exists in the material. If the band gap is about 2 electron-volt wide, only long wavelengths, infrared, and the red part of the visible spectrum are transmitted. On the other hand, a band gap of about 3 electron-volts allows infrared and the entire visible spectrum to be transmitted. If a beam of photons with Hn7 e.g. falls on a semiconductor, there will be some predictable amount of absorption, determined by the properties of the material. We would expect the ratio of transmitted to incident light intensity to depend on the photon wavelength and the thickness of the sample. To calculate this dependence, let us assume that a photon beam of intensity I0, photons centimeter 2 at s, is directed at a sample of thickness L, Fig. 4.2. The beam contains only photons of wavelength L, selected by a monochromator. As the beam passes through the sample, its intensity at a distance x from the surface can be calculated by considering the probability of absorption within any increment dx. Since a photon which has survived to x without absorption has no memory of how far it has traveled, its probability of absorption in any dx is constant. Thus the degradation of the intensity, dx, dx, is proportional to the intensity remaining at x. The solution to this equation is, and the intensity of light transmitted through the sample thickness L is. The coefficient A is called the absorption coefficient and has units of centimeter, 1. This coefficient will of course vary with the photon wavelength and with the material. In a typical plot of a versus wavelength, Fig 4.3, there is negligible absorption at long wavelengths, h and small, and considerable absorption of photons with energies larger than e.g. According to EQ 2.2, the relation between photon energy and wavelength is E equal hcl. If E is given in electron volts and L in micrometers, this becomes E equal 1.24 L. Figure 4.4 indicates the band gap energies of some of the common semiconductors, relative to the visible, infrared, and ultraviolet portions of the spectrum. We observe that gallium arsenide, silicon, germanium, and indium antimonide lie outside the visible region, in the infrared. Other semiconductors, such as gallium phosphide and cadmium sulfide, have band gaps wide enough to pass photons in the visible range. It is important to note here that a semiconductor absorbs photons with energies equal to the band gap, or larger. Thus silicon absorbs not only band gap light, around 1 micrometer, but also shorter wavelengths, including those in the visible part of the spectrum. Figure 4.3. Dependence of optical absorption coefficient A for a semiconductor on the wavelength of incident light. Figure 4.4. Band gaps of some common semiconductors relative to the optical spectrum. When electron-hole pairs are generated in a semiconductor, or when carriers are excited into higher impurity levels from which they fall to their equilibrium states, light can be given off by the material. Many of the semiconductors are well suited for light emission, particularly the compound semiconductors with direct band gaps. The general property of light emission is called luminescence. This overall category can be subdivided according to the excitation mechanism. If carriers are excited by photon absorption, the radiation resulting from the recombination of the excited carriers is called photoluminescence. If the excited carriers are created by high-energy electron bombardment of the material, the mechanism is called cathodoluminescence. If the excitation occurs by the introduction of current into the sample, the resulting luminescence is called electroluminescence. Other types of excitation are possible, but these three are the most important for device applications. The emission processes considered here should not be confused with radiation due to incandescence, which occurs in heated materials. The various luminescent mechanisms can be considered cold processes as compared to the hot process of incandescence, which increases with temperature. In fact, most luminescent processes become more efficient as the temperature is lowered. Photoluminescence. The simplest example of light emission from a semiconductor occurs for direct excitation and recombination of an electron-hole pair, EHP, as depicted in Fig 3.5a. If the recombination occurs directly rather than via a defect level, band gap light is given off in the process. For steady-state excitation, the recombination of electron-hole pairs occurs at the same rate as the generation, and one photon is emitted for each photon absorbed. Direct recombination is a fast process. The mean lifetime of the electron-hole pair is usually on the order of 10 nanoseconds or less. Thus the emission of photons stops within approximately 10 nanoseconds after the excitation is turned off. Such fast luminescent processes are often referred to as fluorescence. In some materials, however, emission continues for periods up to seconds or minutes after the excitation is removed. These slow processes are called phosphorescence, and the materials are called phosphors. An example of a slow process is shown in Fig 4.5. This material contains a defect level, perhaps due to an impurity in the band gap which has a strong tendency to temporarily capture, trap, electrons from the conduction band. The events depicted in the figure are as follows: A. An incoming photon with Hn17 Eg is absorbed, creating an electron-hole pair. B. The excited electron gives up energy to the lattice by scattering until it nears the bottom of the conduction band. C. The electron is trapped by the impurity level ET and remains trapped until it can be thermally re-excited to the conduction band. D. E. Finally, direct recombination occurs as the electron falls to an empty state in the valence band, giving off a photon, Hn2, of approximately the band gap energy. The delay time between excitation and recombination can be relatively long if the probability of thermal re-excitation from the trap, D, is small. Even longer delay times result if the electron is retrapped several times before recombination. If the trapping probability is greater than the probability of recombination, an electron may make several trips between the trap and the conduction band before recombination finally occurs. In such material, the emission of phosphorescent light persists for a relatively long time after the excitation is removed. Figure 4.5. Excitation and recombination mechanisms in photoluminescence with a trapping level for electrons. The color of light emitted by a phosphor such as zinc sulfide depends primarily on the impurities present, since many radiative transitions involve impurity levels within the band gap. This selection of colors is particularly useful in the fabrication of a color television screen. One of the most common examples of photoluminescence is the fluorescent lamp. Typically, such a lamp is composed of a glass tube filled with gas, for example, a mixture of argon and mercury, with a fluorescent coating on the inside of the tube. When an electric discharge is induced between electrodes in the tube, the excited atoms of the gas emit photons, largely in the visible and ultraviolet regions of the spectrum. This light is absorbed by the luminescent coating, and the visible photons are emitted. The efficiency of such a lamp is considerably better than that of an incandescent bulb, and the wavelength mixture in light given off can be adjusted by proper selection of the fluorescent material. Example 4.1. A 0.46 mm thick sample of gallium arsenide is illuminated with monochromatic light of HV equal to electron volts. The absorption coefficient is 50,000 photons per centimeter. The power incident on the sample is 10 milliwatts. A. Find the total energy absorbed by the sample per second, Js. B. Find the rate of excess thermal energy given up by the electrons to the lattice before recombination, Js. C. Find the number of photons per second given off from recombination events, assuming perfect quantum efficiency. Figure 4.6. Excitation and band-to-band recombination leading to photoluminescence. Thus the absorbed power is 9 milliwatts. The fraction of each photon energy unit which is converted to heat is 0.285. Thus the amount of energy converted to heat per second is 2.57 millijoules per second. Assuming one emitted photon for each photon absorbed, perfect quantum efficiency, we have 2.81 times 10 billion times million photons. Electroluminescence. There are many ways by which electrical energy can be used to generate photon emission in a solid. In light-emitting diodes, an electric current causes the injection of minority carriers into regions of the crystal where they can recombine with majority carriers, resulting in the emission of recombination radiation. This important effect, injection electroluminescence, will be discussed in Chapter 8 in terms of p-n junction theory. The first electroluminescent effect to be observed was the emission of photons by certain phosphors in an alternating electric field, the d'Est-Rioux effect. In this device, a phosphor powder such as zinc sulfide is held in a binder material, often a plastic, of a high dielectric constant. When an AC electric field is applied, light is given off by the phosphor. Such cells can be useful as lighting panels, although their efficiency has thus far been too low for most applications and their reliability is poor. Carrier lifetime and photoconductivity. When excess electrons and holes are created in a semiconductor, there is a corresponding increase in the conductivity of the sample as indicated by EQ. 343. If the excess carriers arise from optical luminescence, the resulting increase in conductivity is called photoconductivity. This is an important effect, with useful applications in the analysis of semiconductor materials and in the operation of several types of devices. In this section we shall examine the mechanisms by which excess electrons and holes recombine and apply the recombination kinetics to the analysis of photoconductive devices. However, the importance of recombination is not limited to cases in which the excess carriers are created optically. In fact, virtually every semiconductor device depends in some way on the recombination of excess electrons and holes. Therefore, the concepts developed in this section will be used extensively in the analyses of diodes, transistors, lasers, and other devices in later chapters. Direct recombination of electrons and holes. It was pointed out in section 3.1.4 that electrons in the conduction band of a semiconductor may make transitions to the valence band, i.e., recombine with holes in the valence band, either directly or indirectly. In direct recombination, an excess population of electrons and holes decays by electrons falling from the conduction band to empty states, holes, in the valence band. Energy lost by an electron in making the transition is given up as a photon. Direct recombination occurs spontaneously, that is, the probability that an electron and a hole will recombine is constant in time. As in the case of carrier scattering, this constant probability leads us to expect an exponential solution for the decay of the excess carriers. In this case, the rate of decay of electrons at any time t is proportional to the number of electrons remaining at t and the number of holes, with some constant of proportionality for recombination, AR. The net rate of change in the conduction band electron concentration is the thermal generation rate AR and 2I from EQ. 37, minus the recombination rate. Let us assume the excess electron hole population is created at t equals 0, for example by a short flash of light, and the initial excess electron and hole concentrations N and P are equal 3. Then as the electrons and holes recombine in pairs, the instantaneous concentrations of excess carriers N, T, and P, T, are also equal. Thus we can write the total concentrations of EQ. 44, in terms of the equilibrium values N0 and P0 and the excess carrier concentrations Dn, T, equal dP, T. Using EQ. 324, we will use Dn, T, and dP, T, to mean instantaneous excess carrier concentrations, and N, P for their values at t equals 0. Later we will use similar symbolism for spatial distributions, such as Dn, x, and N, x equals 0. This nonlinear equation would be difficult to solve in its present form. Fortunately, it can be simplified for the case of low-level injection. If the excess carrier concentrations are small, we can neglect the N2 term. Furthermore, if the material is extrinsic, we can usually neglect the term representing the equilibrium minority carriers. For example, if the material is p-type, P0WN0, EQ. 45, becomes. The solution to this equation is an exponential decay from the original excess carrier concentration N. Excess electrons in a p-type semiconductor recombine with a decay constant Vn equal, ARP0, 1, called the recombination lifetime. Since the calculation is made in terms of the minority carriers, Vn is often called the minority carrier lifetime. The decay of excess holes in N-type material occurs with Vp equal, ARN0, 1. In the case of direct recombination, the excess majority carriers decay at exactly the same rate as the minority carriers. There is a large percentage change in the minority carrier electron concentration in example 4.2 and a small percentage change in the majority hole concentration. Basically, the approximations of extrinsic material and low-level injection allow us to represent N, T, in EQ. 44, by the excess concentration at N, T, and P, T, by the equilibrium value P0. Figure 4-7 indicates that this is a good approximation for the example. A more general expression for the carrier lifetime is. This expression is valid for N, or P-type material if the injection level is low. Example 4.2. A numerical example may be helpful in visualizing the approximations made in the analysis of direct recombination. Let us assume a sample of gallium arsenide is doped with 1015 acceptors per cubic centimeter. The intrinsic carrier concentration of gallium arsenide is approximately 1 million per cubic centimeter, thus the minority electron concentration is N0 equal Ni2 is greater than P0 equal 1 milli-electron per cubic centimeter. Certainly the approximation of positron concentration is much greater than electron concentration is valid in this case. Now if 100 trillion electron hole pairs per cubic centimeter are created at T equals 0, we can calculate the decay of these carriers in time. The approximation of dNVP0 is reasonable, as Fig. 4.7 indicates. This figure shows the decay in time of the excess populations for a carrier recombination lifetime of electrons equal lifetime of holes equal 10 nanoseconds. Figure 4.7. Decay of excess electrons and holes by recombination, for change of electrons equal change of holes equal 0.1 P0, with number of electrons negligible, and time equal 10 nanoseconds, example 4.2. The exponential decay of dN, T, is linear on this semi-logarithmic graph. Indirect recombination trapping. In column 4 semiconductors and in certain compounds, the probability of direct electron-hole recombination is very small, Appendix 3. There is some band gap light given off by materials such as silicon and germanium during recombination, but this radiation is very weak and may be detected only by sensitive equipment. The vast majority of the recombination events in indirect materials occur via recombination levels within the band gap, and the resulting energy loss by recombining electrons is usually given up to the lattice as heat rather than by the emission of photons. Any impurity or lattice defect can serve as a recombination center if it is capable of receiving a carrier of one type and subsequently capturing the opposite type of carrier, thereby annihilating the pair. For example, Fig. 4.8 illustrates a recombination level ER which is below F at equilibrium and therefore is substantially filled with electrons. When excess electrons and holes are created in this material, each electron-hole pairs recombines at E, R, in two steps, A, hole capture and, B, electron capture. Figure 4.8. Capture processes at a recombination level, A, hole capture at a filled recombination center, B, electron capture at an empty center. Since the recombination centers in Fig. 4.8 are filled at equilibrium, the first event in the recombination process is hole capture. It is important to note that this event is equivalent to an electron at ER falling to the valence band, leaving behind an empty state in the recombination level. Thus in hole capture, energy is given up as heat to the lattice. Similarly, energy is given up when a conduction band electron subsequently falls to the empty state in ER. When both of these events have occurred, the recombination center is back to its original state, filled with an electron, but an electron-hole pairs is missing. Thus one electron-hole pairs recombination has taken place, and the center is ready to participate in another recombination event by capturing a hole. The carrier lifetime resulting from indirect recombination is somewhat more complicated than is the case for direct recombination, since it is necessary to account for unequal times required for capturing each type of carrier. In particular, recombination is often delayed by the tendency for a captured carrier to be thermally re-excited to its original band before capture of the opposite type of carrier can occur, section 4.2.1. For example, if electron capture, B, does not follow immediately after hole capture, A, in Fig. 4.8, the hole may be thermally re-excited to the valence band. Energy is required for this process, which is equivalent to a valence band electron being raised to the empty state in the recombination level. This process delays the recombination, since the whole must be captured again before recombination can be completed. When a carrier is trapped temporarily at a center and then is re-excited without recombination taking place, the process is often called temporary trapping. Although the nomenclature varies somewhat, it is common to refer to an impurity or defect center as a trapping center, or simply trap, if, after capture of one type of carrier, the most probable next event is re-excitation. If the most probable next event is capture of the opposite type of carrier, the center is predominantly a recombination center. The recombination can be slow or fast, depending on the average time the first carrier is held before the second carrier is captured. In general, trapping levels located deep in the band gap are slower in releasing trapped carriers than are the levels located near one of the bands. This results from the fact that more energy is required, for example, to re-excite a trapped electron from a center near the middle of the gap to the conduction band than is required to re-excite an electron from a level closer to the conduction band. As an example of impurity levels in semiconductors, Fig 494 shows the energy level positions of various impurities in silicon. In this diagram, a superscript indicates whether the impurity is positive, donor, or negative, acceptor, when ionized. Some impurities introduce multiple levels in the band gap. For example, zinc introduces a level, zinc negative, located 0.31 electron volts above the valence band, and a second level, zinc more negative, near the middle of the gap. Each zinc impurity atom is capable of accepting 2 electrons from the semiconductor, one in the lower level and then one in the upper level. The effects of recombination and trapping can be measured by a photoconductive decay experiment. As Fig 47 shows, a population of excess electrons and holes disappears with a decay constant characteristic of the particular recombination process. The conductivity of the sample during the decay is. Therefore, the time dependence of the carrier concentrations can be monitored by recording the sample resistance as a function of time. Figure 49 energy levels of impurities in silicon. The energies are measured from the nearest band edge, energy level of valence band or energy level of conduction band. Donor levels are designated by a plus sign and acceptors by a minus sign. Figure 410 experimental arrangement for photoconductive decay measurements, and a typical oscilloscope trace. A typical experimental arrangement is shown schematically in Fig 410. A source of short pulses of light is required, along with an oscilloscope for displaying the sample voltage as the resistance varies. Microsecond light pulses can be obtained by periodically discharging a capacitor through a flash tube containing a gas such as xenon. For shorter pulses, special techniques such as the use of a pulsed laser must be used. Steady-state carrier generation, quasi-Fermi levels. In the previous discussion we emphasized the transient decay of an excess electron-hole pairs population. However, the various recombination mechanisms are also important in a sample at thermal equilibrium or with a steady-state electron-hole pairs generation recombination, GR, balance. 5. For example, a semiconductor at equilibrium experiences thermal generation of electron-hole pairs at a rate g, t, equal gi described by EQ. 3.7. This generation is balanced by the recombination rate so that the equilibrium concentrations of carriers N0 and P0 are maintained. This equilibrium rate balance can include generation from defect centers as well as band-to-band generation. If a steady light is shown on the sample, an optical generation rate GOP will be added to the thermal generation, and the carrier concentrations N and P will increase to new steady-state values. We can write the balance between generation and recombination in terms of the equilibrium carrier concentrations and the departures from equilibrium Fn and Fp. For steady-state recombination and no trapping, N equal P, thus EQ. 4.11, becomes. The term equilibrium refers to a condition of no external excitation except for temperature, and no net motion of charge, for example, a sample at a constant temperature, in the dark, with no fields applied. Steady state refers to an equilibrium condition in which all processes are constant and are balanced by opposing processes, for example, a sample with a constant current or a constant optical generation of electron-hole pairs just balanced by recombination. The term Rn0P0 is just equal to the thermal generation rate G, T. Thus, neglecting the at N2 term for low-level excitation, we can rewrite EQ 412 as the excess carrier concentration can be written as. More general expressions are given in EQ 416, which allow for the case hole lifetime not equal to electron lifetime, when trapping is present. Example 4-3. As a numerical example, let us assume that 10 trillion electron-hole pairs per cubic centimeter are created. Example 4-3. Optically every microsecond in a silicon sample with 100 trillions of charge carriers per cubic centimeter and number of electrons equals number of holes. The steady-state excess electron, or hole, concentration is then 20 trillion per cubic centimeter. While the percentage change in the majority electron concentration is small, the minority carrier concentration changes from 2. The steady-state electron concentration is where caret equals 0.0259 electron volts at room temperature. Thus the electron quasi-Fermi level position Fn, EI is found from Nf. N lies 0.233 electron volts above the intrinsic level. By a similar calculation, the whole quasi-Fermi level lies 0.186 electron volts below EI, Fig 411. In this example, the equilibrium Fermi level is 0.0259 Ln, 6.67 103, equals 0.228 electron volts above the intrinsic level. Figure 411. Quasi-Fermi levels Fn and Fp for a silicon sample with number of charged particles equal 100 trillion per cubic centimeter, positron lifespan equal 2 microseconds, and million trillions of electron-hole pairs per cubic centimeter. Example 4.4. It is often desirable to refer to the steady-state electron and hole concentrations in terms of Fermi levels, which can be included in band diagrams for various devices. The Fermi level used in EQ 325 is meaningful only when no excess carriers are present. However, we can write expressions for the steady-state concentrations in the same form as the equilibrium expressions by defining separate quasi-Fermi levels Fn and Fp for electrons and holes. The resulting carrier concentration equations can be considered as defining relations for the quasi-Fermi levels. The quasi-Fermi levels of Fig 411 illustrate dramatically the deviation from equilibrium caused by the optical excitation. The steady-state Fn is only slightly above the equilibrium F, whereas Fp is greatly displaced below. From the figure it is obvious that the excitation causes a large percentage change in minority carrier hole concentration and a relatively small change in the electron concentration. In summary, the quasi-Fermi levels Fn and Fp are the steady-state analogues of the equilibrium Fermi level F. When excess carriers are present, the deviations of electron energy level and positron energy level from Fermi energy level indicate how far the electron and hole populations are from the equilibrium values N0 and P0. A given concentration of excess electron-hole pairs causes a large shift in the minority carrier quasi-Fermi level compared with that for the majority carriers. The separation of the quasi-Fermi levels Fn, Fp is a direct measure of the deviation from equilibrium. At equilibrium Fn equal Fp equal F. The concept of quasi-Fermi levels is very useful in visualizing minority and majority carrier concentrations in devices where these quantities vary with position. Photoconductive devices. There are a number of applications for devices which change their resistance when exposed to light. For example, such light detectors can be used in the home to control automatic night lights which turn on at dusk and turn off at dawn. They can also be used to measure illumination levels, as in exposure meters for cameras. Many systems include a light beam aimed at the photoconductor, which signals the presence of an object between the source and detector. Such systems are useful in moving object counters, burglar alarms, and many other applications. Detectors are used in optical signaling systems in which information is transmitted by a light beam and is received at a photoconductive cell. Considerations in choosing a photoconductor for a given application include the sensitive wavelength range, time response, and optical sensitivity of the material. In general, semiconductors are most sensitive to photons with energies equal to the band gap or slightly more energetic than band gap. Less energetic photons are not absorbed, and photons with HNEG are absorbed at the surface and contribute little to the bulk conductivity. Therefore, the table of band gaps, Appendix 3, indicates the photon energies to which most semiconductor photodetectors respond. For example, cadmium sulfide, e.g. equal 2.42 electron volts, is commonly used as a photoconductor in the visible range, and narrowgap materials such as germanium, 0.67 electron volts, and indium antimonide, 0.18 electron volts, are useful in the infrared portion of the spectrum. Some photoconductors respond to excitations of carriers from impurity levels within the band gap and therefore are sensitive to photons of less than band gap energy. The optical sensitivity of a photoconductor can be evaluated by examining the steady-state excess carrier concentrations generated by an optical generation rate GOP. If the mean time each carrier spends in its respective band before capture is electron lifespan and positron lifespan, we have, and the photoconductivity change is. For simple recombination, Vn and Vp will be equal. If trapping is present, however, one of the carriers may spend little time in its band before being trapped. From EQ 417, it is obvious that for maximum photoconductive response, we want high mobilities and long lifetimes. Some semiconductors are especially good candidates for photoconductive devices because of their high mobility. For example, indium antimonide has an electron mobility of about 500,000 cm per volt seconds and therefore is used as a sensitive infrared detector in many applications. The time response of a photoconductive cell is limited by the recombination times, the degree of carrier trapping, and the time required for carriers to drift through the device in an electric field. Often these properties can be adjusted by proper choice of material and device geometry, but in some cases improvements in response time are made at the expense of sensitivity. For example, the drift time can be reduced by making the device short, but this substantially reduces the responsive area of the device. In addition, it is often desirable that the device have a large dark resistance, and for this reason, shortening the length may not be practical. There is usually a compromise between sensitivity, response time, dark resistance, and other requirements in choosing a device for a particular application. When excess carriers are created non-uniformly in a semiconductor, the electron and hole concentrations vary with position in the sample. Any such spatial variation, gradient, in N and P calls for a net motion of the carriers from regions of high carrier concentration to regions of low carrier concentration. This type of motion is called diffusion and represents an important charge transport process in semiconductors. The two basic processes of current conduction are diffusion due to a carrier gradient and drift in an electric field. Diffusion processes. When a bottle of perfume is opened in one corner of a closed room, the scent is soon detected throughout the room. If there is no convection or other net motion of air, the scent spreads by diffusion. The diffusion is the natural result of the random motion of the individual molecules. Consider, for example, a volume of arbitrary shape with scented air molecules inside and unscented molecules outside the volume. All the molecules undergo random thermal motion and collisions with other molecules. Thus each molecule moves in an arbitrary direction until it collides with another air molecule, after which it moves in a new direction. If the motion is truly random, a molecule at the edge of the volume has equal probabilities of moving into or out of the volume on its next step, assuming the curvature of the surface is negligible on the molecular scale. Therefore, after a mean free time t, half the molecules at the edge will have moved into the volume and half will have moved out of the volume. The net effect is that the volume containing scented molecules has increased. This process will continue until the molecules are uniformly distributed in the room. Only then will a given volume gain as many molecules as it loses in a given time. In other words, net diffusion will continue as long as gradients exist in the distribution of scented molecules. Carriers in a semiconductor diffuse in a carrier gradient by random thermal motion and scattering from the lattice and impurities. For example, a pulse of excess electrons injected at x equals 0 at time t equals 0 will spread out in time as shown in Fig 412. Initially, the excess electrons are concentrated at x equals 0, as time passes, however, electrons diffuse to regions of low electron concentration until finally n, x, is constant. We can calculate the rate at which the electrons diffuse in a one-dimensional problem by considering an arbitrary distribution n, x, such as Fig 413a. Since the mean free path L between collisions is a small incremental distance, we can divide x into segments L wide, with n, x, evaluated at the center of each segment, Fig 413b. An arbitrary electron concentration gradient in one dimension, a, division of n, x, into segments of length equal to a mean free path for the electrons, b, expanded. View of two of the segments centered at x0. The electrons in segment 1, to the left of x0 in Fig 413b have equal chances of moving left or right, and in a mean free time t1 half of them will move into segment 2. The same is true of electrons within one mean free path of x0 to the right, one half of these electrons will move through x0 from right to left in a mean free time. Therefore, the net number of electrons passing x0 from left to right in one mean free time is 1 2, n1 La, 1 2, n2 La, where the area perpendicular to x is a. The rate of electron flow in the plus x direction per unit area, the electron flux density Hn, is given by. Since the mean free path L is a small differential length, the difference in electron concentration, n1, n2, can be written as where x is taken at the center of segment 1, and x equal L. In the limit of small x, i.e., small mean free path L between scattering collisions, EQ. 418, can be written in terms of the carrier gradient dn, x, dx. The quantity L22T is called the electron diffusion coefficient 7dn, with units centimeters per second. The minus sign in EQ. 420, arises from the definition of the derivative. It simply indicates that the net motion of electrons due to diffusion is in the direction of decreasing electron concentration. This is the result we expect, since net diffusion occurs from regions of high particle concentration to regions of low particle concentration. By identical arguments, we can show that holes in a hole concentration gradient move with a diffusion coefficient dp. Thus, the diffusion current crossing a unit area, the current density, is the particle flux density multiplied by the charge of the carrier. It is important to note that electrons and holes move together in a carrier gradient EQs. 421, but the resulting currents are in opposite directions EQs. 422, because of the opposite charge of electrons and holes. Diffusion and drift of carriers, built-in fields. If an electric field is present in addition to the carrier gradient, the current densities will each have a drift component and a diffusion component. And the total current density is the sum of the contributions due to electrons and holes. Figure 414. Drift and diffusion directions for electrons and holes in a carrier gradient and an electric field. Particle flow directions are indicated by dashed arrows, and the resulting currents are indicated by solid arrows. We can best visualize the relation between the particle flow and the current of EQs. 423, by considering a diagram such as shown in Fig 414. In this figure an electric field is assumed to be in the x direction, along with carrier distributions n, x, and p, x, which decrease with increasing x. Thus the derivatives in EQs 421 are negative, and diffusion takes place in the plus x direction. The resulting electron and hole diffusion currents Gn, div, and Jp, div, are in opposite directions, according to EQs. 422. Holes drift in the direction of the electric field Hp, drift, whereas electrons drift in the opposite direction because of their negative charge. The resulting drift current is in the plus x direction in each case. Note that the drift and diffusion components of the current are additive for holes when the field is in the direction of decreasing hole concentration, whereas the two components are subtractive for electrons under similar conditions. The total current may be due primarily to the flow of electrons or holes, depending on the relative concentrations and the relative magnitudes and directions of electric field and carrier gradients. An important result of EQs. 423, is that minority carriers can contribute significantly to the current through diffusion. Since the drift terms are proportional to carrier concentration, minority carriers seldom provide much drift current. On the other hand, diffusion current is proportional to the gradient of concentration. For example, in N-type material the minority hole concentration P may be many orders of magnitude smaller than the electron concentration N, but the gradient dP dx may be significant. As a result, minority carrier currents through diffusion can sometimes be as large as majority carrier currents. In discussing the motion of carriers in an electric field, we should indicate the influence of the field on the energies of electrons in the band diagrams. Assuming an electric field, x, in the x direction, we can draw the energy bands as in Fig 415, to include the change in potential energy of electrons in the field. Since electrons drift in a direction opposite to the field, we expect the potential energy for electrons to increase in the direction of the field, as in Fig 415. The electrostatic potential, x, varies in the opposite direction, since it is defined in terms of positive charges and is therefore related to the electron potential energy E, x, displayed in the figure by Figure 415. Energy band diagram of a semiconductor in an electric field, x. From the definition of electric field, we can relate x to the electron potential energy in the band diagram by choosing some reference in the band for the electrostatic potential. We are interested only in the spatial variation, x, for EQ. 425. Choosing EI as a convenient reference, we can relate the electric field to this reference by. Therefore, the variation of band energies with x, as drawn in Fig 415 is correct. The direction of the slope in the bands relative to is simple to remember, since the diagram indicates electron energies, we know the slope in the bands must be such that electrons drift downhill in the field. Therefore, points uphill in the band diagram. At equilibrium, no net current flows in a semiconductor. Thus any fluctuation which would begin a diffusion current also sets up an electric field which redistributes carriers by drift. An examination of the requirements for equilibrium indicates that the diffusion coefficient and mobility must be related. Setting EQ 423b, equal to 0 for equilibrium, we have Table 4:1 diffusion coefficient and mobility of electrons and holes for intrinsic semiconductors at 300 K. Note, use Fig 323 for doped semiconductors. Electron diffusion coefficient in germanium 100 cm per second. Hole diffusion coefficient in germanium 50 cm per second. Electron mobility in germanium 3900 cm per volt seconds. Hole mobility in germanium 1900 cm per volt seconds. Electron diffusion coefficient in silicon 35 cm per second. Hole diffusion coefficient in silicon 12.5 cm per second. Electron mobility in silicon 1350 cm per volt seconds. Hole mobility in silicon 480 cm per volt seconds. Electron diffusion coefficient in gallium arsenide 220 cm per second. Hole diffusion coefficient in gallium arsenide 10 cm per second. Electron mobility in gallium arsenide 8500 cm per volt second. Hole mobility in gallium arsenide 400 cm per volt second. The equilibrium Fermi level does not vary with x, and the derivative of EI is given by EQ. 426. Thus EQ 428 reduces to. This result is obtained for either carrier type. This important equation is called the Einstein relation. It allows us to calculate either D or O from a measurement of the other. Table 4:1 lists typical values of D and O for several semiconductors at room temperature. It is clear from these values that DO 0.026 V. An important result of the balance of drift and diffusion at equilibrium is that built-in fields accompany gradients in EICEQ. 426. Such gradients in the bands at equilibrium, F constant, can arise when the band gap varies due to changes in alloy composition. More commonly, built-in fields result from doping gradients. For example, a donor distribution D, X, causes a gradient in N0, X, which must be balanced by a built-in electric field, X. Diffusion and recombination, the continuity equation. In the discussion of diffusion of excess carriers, we have thus far neglected the important effects of recombination. These effects must be included in a description of conduction processes, however, since recombination can cause a variation in the carrier distribution. For example, consider a differential length, x, of a semiconductor sample with area A in the YZ plane, Fig. 416. The whole current density leaving the volume, Jp, x plus x, can be larger or smaller than the current density entering, Jp, x, depending on the generation and recombination of carriers taking place within the volume. The net increase in hole concentration per unit time, 0p0t, is the difference between the hole flux per unit volume entering and leaving, minus the recombination rate. We can convert hole current density to hole particle flux density by dividing Jp by Q. The current densities are already expressed per unit area, thus dividing Jp, x, Q by, x, gives the number of carriers per unit volume entering xa per unit time, and 1q, Jp, x plus x, x is the number leaving per unit volume and time. Figure 416. Current entering and leaving a volume xa. As x approaches 0, we can write the current change in derivative form. The expression, 431a, is called the continuity equation for holes. For electrons we can write. Since the electronic charge is negative, when the current is carried strictly by diffusion, negligible drift, we can replace the currents in EQs. 431, by the expressions for diffusion current, for example, for electron diffusion we have. Substituting this into EQ. 431b, we obtain the diffusion equation for electrons. And similarly for holes. These equations are useful in solving transient problems of diffusion with recombination. For example, a pulse of electrons in a semiconductor, Fig. 412, spreads out by diffusion and disappears by recombination. 2. Solve for the electron distribution in time, n, x, t, we would begin with the diffusion equation, EQ. 433a. Steady-state carrier injection, diffusion length. In many problems a steady-state distribution of excess carriers is maintained, such that the time derivatives in EQs 433 are 0. In the steady-state case the diffusion equations become, where L is called the electron diffusion length and Lp is the diffusion length for holes. We no longer need partial derivatives, since the time variation is 0 for steady state. The physical significance of the diffusion length can be understood best by an example. Let us assume that excess holes are somehow injected into a semi-infinite semiconductor bar at x equals 0, and the steady-state hole injection maintains a constant excess hole concentration at the injection point Fp, x equals 0, equal p. The injected holes diffuse along the bar, recombining with a characteristic lifetime Vp. In steady state we expect the distribution of excess holes to decay to 0 for large values of x, because of the recombination, Fig. 417. For this problem we use the steady-state diffusion equation for holes, EQ. 434b. The solution to this equation has the form. We can evaluate C1 and C2 from the boundary conditions. Since recombination must reduce dp, x, to 0 for large values of x, Fp equals 0 at x equal and therefore C1 equals 0. Similarly, the condition Fp equal p at x equals 0 gives C2 equal p, and the solution is Figure 417. Injection of holes at x equals 0, giving a steady-state hole distribution p, x, and a resulting diffusion current density Jp, x. The injected excess hole concentration dies out exponentially in x due to recombination, and the diffusion length Lp represents the distance at which the excess hole distribution is reduced to 1/e of its value at the point of injection. We can show that Lp is the average distance a hole diffuses before recombining. To calculate an average diffusion length, we must obtain an expression for the probability that an injected hole recombines in a particular interval dx. The probability that a hole injected at x equals 0 survives to x without recombination is Fp, x, p equal exp, xlp, the ratio of the steady-state concentrations at x and 0. On the other hand, the probability that a hole at x will recombine in the subsequent interval dx is. Thus the total probability that a hole injected at x equals 0 will recombine in a given dx is the product of the two probabilities. Then, using the usual averaging techniques described by EQ. 221, the average distance a hole diffuses before recombining is. The steady-state distribution of excess holes causes diffusion, and therefore a hole current, in the direction of decreasing concentration. From EQs 422b, and 436, we have. Since p, x, equal p0 plus dp, x, the space derivative involves only the excess concentration. We notice that since Fp, x, is proportional to its derivative for an exponential distribution, the diffusion current at any x is just proportional to the excess concentration Fp at that position. Although this example seems rather restricted, its usefulness will become apparent in Chapter 5 in the discussion of p-n junctions. The injection of minority carriers across a junction often leads to exponential distributions as in EQ. 436, with the resulting diffusion current of EQ. 440. Example 4.4. In a very long p-type silicon bar with cross-sectional area equal 0.5 square centimeters and number of acceptors equal 10 million billion per cubic centimeter, we inject holes such that the steady-state excess hole concentration is 50 million billions per cubic centimeter. What is the steady-state separation between Fp and Ec at x equal 1000 angstroms? What is the hole current there? How much is the excess stored hole charge? Assume that hole mobility equal 500 cm per volt seconds and hole lifespan equal 1 nanosecond. The Haynes-Shockley experiment. One of the classic semiconductor experiments is the demonstration of drift and diffusion of minority carriers, first performed by J.R. Haynes and W. Shockley in 1951 at the Bell Telephone Laboratories. The experiment allows independent measurement of the minority carrier mobility m and diffusion coefficient d. The basic principles of the Haynes-Shockley experiment are as follows: a pulse of holes is created in an n-type bar, for example, that contains an electric field, Fig. 418, as the pulse drifts in the field and spreads out by diffusion, the excess hole concentration is monitored at some point down the bar. The time required for the holes to drift a given distance and the field gives a measure of the mobility. The spreading of the pulse during a given time is used to calculate the diffusion coefficient. In Fig. 418 a pulse of excess carriers is created by a light flash at some point x equals 0 in an n-type semiconductor, electrons more than holes. We assume that the excess carriers have a negligible effect on the electron concentration but change the hole concentration significantly. The excess holes drift in the direction of the electric field and eventually reach the point x equal L, where they are monitored. By measuring the drift time Td, we can calculate the drift velocity Vd and, therefore, the hole mobility. Thus the hole mobility can be calculated directly from a measurement of the drift time for the pulse as it moves down the bar. In contrast with the Hall effect, section 3.4.5, which can be used with resistivity to obtain the majority carrier mobility, the Haynes-Shockley experiment is used to measure the minority carrier mobility. As the pulse drifts in the field, it also spreads out by diffusion. By measuring the spread in the pulse, we can calculate dP. To predict the distribution of holes in the pulse as a function of time, let us first re-examine the case of diffusion of a pulse without drift, neglecting recombination, Fig. 4.12. The equation which the hole distribution must satisfy is the time-dependent diffusion equation, EQ. 433b. For the case of negligible recombination, Vp long compared with the times involved in the diffusion, we can write the diffusion equation as: the function which satisfies this equation is called a Gaussian distribution, where p is the number of holes per unit area created over a negligibly small distance at t equals 0. The factor in brackets indicates that the peak value of the pulse, at x equals 0, decreases with time, and the exponential factor predicts the spread of the pulse in the positive and negative x directions, Fig. 4.19. If we designate the peak value of the pulse as fp9 at any time, say Td, we can use EQ. 444, to calculate dP from the value of p at some point x. The most convenient choice is the point x2, at which p is down by 1e of its peak value p9. At this point we can write. Since x cannot be measured directly, we use an experimental setup such as Fig. 420, which allows us to display the pulse on an oscilloscope as the carriers pass under a detector. As we shall see in Chapter 5, a forward-biased PN junction serves as an excellent injector of minority carriers, and a reverse-biased junction serves as a detector. The measured quantity in Fig. 420 is the pulse width T displayed on the oscilloscope in time. It is related to x by the drift velocity, as the pulse drifts past the detector point, 2. Figure 419. Calculation of positron diffusion coefficient from the shape of the positron distribution after time Td. No drift or recombination is included. Figure 420. The Haynes-Shockley experiment, A. Circuit schematic, B. Typical trace on the oscilloscope screen. Example 4.5. An N-type germanium sample is used in the Haynes-Shockley experiment shown in Fig. 420. The length of the sample is 1 cm, and the probes, 1, and 2, are separated by 0.95 cm. The battery voltage E0 is 2V. A pulse arrives at point 2, 0.25 ms after injection at 1, the width of the pulse T is 117 ms. Calculate the hole mobility and diffusion coefficient, and check the results against the Einstein relation. Gradients in the quasi-Fermi levels. In section 3.5 we saw that equilibrium implies no gradient in the Fermi level F. In contrast, any combination of drift and diffusion implies a gradient in the steady-state quasi-Fermi level. We can use the results of EQs 423, 426, and 429, to demonstrate the power of the concept of quasi-Fermi levels in semiconductors. CEQ 415. If we take the general case of non-equilibrium electron concentration with drift and diffusion, we must write the total electron current as where the gradient in electron concentration is. Using the Einstein relation, the total electron current becomes. But EQ 426 indicates that the subtractive term in the brackets is just Q, x, giving a direct cancellation of QMNN, x, x, and leaving. Thus, the processes of electron drift and diffusion are summed up by the spatial variation of the quasi-Fermi level. The same derivation can be made for holes, and we can write the current due to drift and diffusion in the form of a modified Ohm's law. Therefore, any drift, diffusion, or combination of the two in a semiconductor results in currents proportional to the gradients of the two quasi-Fermi levels. Conversely, a lack of current implies constant quasi-Fermi levels. One can use a hydrostatic analogy for quasi-Fermi levels and identify it as water pressure in a system. Just as water flows from a high-pressure region to a low-pressure region, until in equilibrium the water pressure is the same everywhere, similarly electrons flow from a high to low electron quasi-Fermi level region, until we get a flat Fermi level in equilibrium. Quasi-Fermi levels are sometimes also known as electrochemical potentials because, as we just saw, the driving force for carriers is governed partly by gradients of electrical potential, or electric field, which determines drift, and partly by gradients of carrier concentration, which is related to a thermodynamic concept called chemical potential, giving rise to diffusion. Summary: excess carriers, above the equilibrium values contributed by doping, may be created optically, or by electrical biasing in devices. Generation recombination, GR, of electron-hole pairs, EHPs, can occur by absorption of the photons with energy greater than the band gap, balanced by direct or indirect recombination. Generation recombination processes can be mediated by traps, especially deep traps near midgap. Band-to-band or trap-assisted GR processes lead to an average lifetime for the excess carriers. Carrier lifetime multiplied by the optical generation rate establishes a steady-state excess population of carriers. The square root of carrier lifetime multiplied by the diffusion coefficient determines the diffusion length. In equilibrium, we have a constant Fermi level. In non-equilibrium with excess carriers, Fermi levels are generalized to separate quasi-Fermi levels for electrons and holes. The quasi-Fermi level splitting is a measure of the departure from equilibrium. Minority carrier quasi-Fermi levels change more than majority carrier quasi-Fermi levels because the relative change of minority carriers is larger. Gradients in the quasi-Fermi level determine the net drift diffusion current. Diffusion flux measures the flow of carriers from high to low concentration regions and is given by the diffusivity times the concentration gradient. The direction of diffusion current is opposite to the flux for the negative electrons, but in the same direction for the positive holes. Carrier diffusivity is related to mobility by the thermal voltage Q, Einstein relation. When carriers move in a semiconductor due to drift or diffusion, the time-dependent carrier concentrations at different points is given by the carrier continuity equation, which says that if more carriers flow into a point than flow out, the concentration will increase as a function of time and vice versa. GR processes also affect carrier concentrations.